Hi, this is Dr. S.P. Arsa from Mechanical and Industrial Department, IIT Roorkee. In the course of vibration control, we discussed about the three modules, and in these three modules, we mainly these were focused on the vibration generation mechanism, how to design the material for suppression of vibration. Then even you see the vibration isolators feature spatially, and because we know that when the vibrations are generated from the source, the transmission is also playing a critical role in that. So whenever we are designing the entire vibration control system, we need to check it out that at the end, when at the receiver, when the vibrations are being transmitted, what exactly the kind of amplitude and the frequency levels are there. Accordingly, we can design these the vibration control system. So in the previous module, we discussed about that what exactly the material feature is. Through that, at least we can put some kind of damping features there itself. So there were various compositions will just came, and you see we know that from the material aspects, you see here there are various internal resonances are also there. So it's not that you see just by taking some kind of good high carbon percentage material, or in the metal side particular, or even such kind of polymers which can absorb the vibration, just take it like that. No, because we know that some internal resonances at the molecular level, even they are just playing a critical role in dislocation of these molecules, and also at one point of time the energies are being released from the system, from the material itself, and which makes the system unstable. So we discussed thoroughly about the material design, that what exactly the design considerations should be there, at least at the point of material chosen for that, from the damping point of view. Because you see there are various other aspects are there in the material side. You see when some kind of the weight considerations are there, the strength considerations are there, against the typical type of load, against the temperature, against the moisture, various phenomena are there. But from this aspect as well, because we know that the vibration generation and the transmission is quite rapid according to the material, so we need to choose the material, so that you see here we can provide the kind of damping from these materials. So in this module, our main focus will be there on the passive vibration control. What exactly the mean of the passive vibration control we already discussed, because there are two main modes or two main mechanisms through which we can control the entire vibration from the machine or the transmission feature through the path towards the outer side. Maybe it is just towards the environment exposure feature. The one part is the passive, which we can directly apply. You see here some external sources are to be added directly, just like you see like the cushion, the rubber, or any kind of plastomers features, and then we can control the things. But which type of the appropriate device should be chosen, so that you see here we can effectively control the noise and the vibration level, and you see we can provide the comfort conditioning towards the production floor people. And then also you see here we can get the accuracy during any machining operations or any kind of operations at the production floor. Second was the active vibration control, in which we need to provide some kind of the electronic forces, in which you see here the direct control can be put at the time of you see the excitation. Not these kind of devices should be provided at that. We will discuss in detail that how we can design these active vibration control and the passive vibration control according to the service condition, according to the environmental features, and according to you see here what exactly the operating features are there at which the sound and vibrations are being generated, and we need to control those right from the source to transmission towards the receiver feature. So now you see here, if we are talking about this, we know that the common accepted method for this in any of these industrial equipment devices, where you see the excitation forces are quite dominating, and then you see here we have a huge vibrations and this noise level is. The first thing is coming to our mind, that how we can reduce the force through which these vibrations are generating. Maybe it is because of the unbalanced force, maybe it is because of the misalignment feature, looseness feature, or any external excitations are there, or maybe the interaction, the nature of forces, if the impulsive or any kind, the flow induced. Then we need to check it out that how we can reduce the force. Second, either can we provide straight damping there itself, can we provide the spring itself, or will it be mass through which we can suppress the vibration. So these are very common methods, like if you are talking to a layman, they can say, why don't we put these things to control that. So in general way, we can say that vibration can be straightway isolated from the equipment using these, either the passive technology by adopting some external devices, or by active technology by reducing the force through electronic manner. And with the active forces, like you see, we are saying that the forces which are quite active at the point of contact, or at the point of you see this misalignment feature, then we can adopt even the active vibration control by creating electronically, like the force using the smart sensors or the actuations with the the smart materials even, to cancel out these unwanted forces which are being coming out through the whatever the machinery features or the rotating part of the machine. So either if we are going towards the passive or the active, we need to first see what is the feasibility and what exactly the kind of excitation level is, and what the entire structure is there, because ultimately the structure is supporting to these vibration features and the sound propagation. So with this passive method, the isolation can be straightway achieved by putting certain isolators, but again you see the basic limitation is coming in that what type of isolator we need to provide to cancel out these unwanted forces. So generally we need to see that what exactly the connection which we can provide from the isolator to the excitation, so that whatever the dissipated or the radiated form of the energy is coming out, it can be straightway absorbed. So that means you see here it is a kind of some structural modifications as we are just going towards the passive control, because in that there is a clear gluing, adding, or any kind of you see fixing of an external device on the surface of vibrations. Or even you see here we can choose some kind of stiffener feature like the like the spring stiffness or the high kind of like any device through which the stiffness can be provided to improve the vibration absorption or the released feature, or the in other way we can say that the vibration response through this vibration control processor. So it is you see like some kind of the technique in which we need to use some kind of the additional device, like in the in the active vibration control technique, we need to add some kind of power or energy in form of some we can say like the actuator, or in some kind of we can say the sensor, and these you see the power is just acting against the generated power, generated force or whatever, to cancel out. But here this is a direct material of the absorber or the isolator which needs to be put on the surface to absorb the energy or to absorb the vibration from excitation level from the source or from the receiving path. So most common, so in this chapter our main feature is the designing part of the absorber or the isolator in the passive manner. So the most common passive vibration control is absorber, because we need to absorb the amount of energy which is being creating by the excitation feature. So most of the work here is being presenting in terms of the damping material which is associated with these absorber, and directly can be applied to the structure where the excitation features are there, so that we can increase the damping ratio at the various excitation modes or the excitation frequencies. Sometimes we can also add the mass or just add the springs to strengthen the stiffness features there. They are also coming under the category of the vibration control. Through that you see here we can at least adjust the resonance frequency, so that you see here we can avoid the huge amount of energy or the amplitude excitation at that frequencies. So the most effective treatment here is the damping treatment, because it increases the rate of decay of vibration, and through that an effective way of vibration control can be adopted. So, passive methods sometimes involve even electromechanical controls for this cancellation of the vibration forces. But you see here, in that also the isolation mechanism is also a kind of passive, some straight adapted feature. So, we can say that either we are using the elastomers, the rubber, or even if we are using any kind of fluid material, even we are using the springs, the fluids are sometimes providing the negative stiffness towards the component as well. So, either of that you see here which we are choosing is coming under the passive control equipment, and then you see here we can straightway put that how we can design either the spring or the elastomers or any kind of rubber polymers and all this part, and also a fluid, or rather we can say the fluid is nothing but which is just providing the negative stiffness. We can say it is also the elastomeric element which we can straightway add to the string this spring element for providing some kind of the integrated effect of the restoring and the damping forces. Just like you see, like nowadays this is the composition of the spring and the damping feature is always coming together, and we are saying that these are somewhat the advanced elastomers which can provide a perfect shock absorber in various vehicles. So, in that you see here the mechanical energy which is like coming from the shock in terms of the impulsive forces or in terms of any abrupt change in the force magnitude, or even the cyclic feature of the vibration can straightway work on the fluid and is converted the thermal energy into the fluid. So, you see here there is a clear reduction of the amount of energy which is being transmitted to the body of the vehicle. So, means that you see here whatever the fluid or any elastomeric element which is being chosen in these cases, they are effectively acting just like you see the absorbing the energy and also the transmission of or the dissipation of energy in such a way that from the source the things can the whatever the excitation can be straightway reduced. So, elastomers generally when we are talking about, these are always a damped feature in which the rubber like materials are there, through which you see we can absorb the mechanical energy under the force due to the deformation. So, elastomeric isolators are sometimes we are saying that you see because of the vehicle at which we are using these elastomeric feature of the element, they are always being used to absorb the shock vibration or the cyclic vibrations. So, whenever you see the shock and these cyclic vibrations are being there in any of the vehicle, these elastomeric isolators are just mounted on the automobile engines or even the aircraft components, the heavy industrial rotating machinery, or even you see nowadays because of the earthquake the random vibrations are coming. So, even the building foundations, these elastomeric isolators are just perfect replacement for these things. So, we cannot rely straightway on the damping feature of concrete and say that yeah, that is perfectly okay when like the earthquake or these tremors are being coming in this way, the random vibration feature. Because rubber does not you see like sometimes rubber does provide you see the energy damping, but it is not you see like it is having a similar kind of characteristic that by only putting the rubber you have the entire features. You need to just go with the elastomeric feature of the damping and you need to add in that way. So, you see here the isolation is having much better in the specific direction, like say the vertical direction the excitation is quite dominant when the vehicles are moving, we need to keep accordingly. So, the most sophisticated passive isolators which using air or negative stiffness technology, because in these recent time of technology we need to go with the interferometry or microscopic, like you see like the SPM, SEM and all these you see the nanofabrication and the micro hardness testing, and with these all advanced technology we can provide a best possible passive vibration isolation device through which we can go up to the highly level, we can say high precise level absorption of the vibrations. Because in that you see here we need to design the passive isolator in such a way that we can use the air as the suspension device, or even sometimes we can say that the negative damping as a suspension device along with these elastomeric features of the rubber. Through that you see here we can effectively control the vibration for such a sophisticated system. Like you see the pneumatic systems which are supporting a heavy table or even the platform on any compressed air pistons, and through that you see here we are just providing a decoupling link between the ground and table. And you see here the entire table, if you look at the real mechanism, the entire table is floating on the air only. So, this air is acting as the passive control feature, and through that this entire you see like the we can say this suspension is being provided by the air, and there is a clear isolation of the table to ground with the using of this compressed air. So, the most sophisticated air tables are always providing a good and the precise operations with just like removing the entire vibration through the isolated floor vibrations and even the small amplitude. But the things are there that what kind of the operations are being requiring the precise operation, because this is one of the expensive method. Because we know that when we are just putting the compressed air, we need to check it out the pressure and the pressure variation in the entire operations there itself. And also you see here we need to check it out what exactly the maintenance features are there to keep the pressure uniform and the same time the leveling of the entire system. So, you see here the entire control strategy is somewhat expensive for such kind of sophisticated system. But at the same time you see here when we are just doing at the low frequency excitations, sometimes this air suspension is not an accurate one. So, we need to go with the other way, that is the negative stiffness features, because you see the air supply system for the pneumatic isolator can sometimes creating even the ambient vibrations also. So, now we will use even some other electrical methods for the leveling of the table and controlling the cylindrical pressure, just to add somewhat more complexity and the potential of the entire system failure. But the negative stiffness isolator, they are providing a simple, a reliable and highly effective isolation solution for the sensitive instrumentation even at the low frequency and the low amplitude of the floor and the building vibrations. And also you see they have a good features that they are relatively small you see as compared to like the compressed air feature. Also they are having the lightweight, they are more stable, and you see here as far as the maintenance and the cost feature is concerned, it is perfectly alright with that. So, again you see here we need to check it out that what kind of applications are there on which the vibration generation and the reductions are to be featured out. So, the first thing is coming, what is the design consideration of the absorber and the isolator under these all dynamic actions of the vibrations. So, we know that the vibration isolation means to reduce the vibration level or the amplitude of vibration in one or several selected areas. So, here we need to hinder the spread of the vibration along the path from the source towards the receiver as we discussed. So, isolation of vibration means you see here it is a clear reduction of the amplitude at the source. At the same time you see we cannot always go for the treatment of the source only, we need to treat this entire structure through that you see here the transmission is quite rapid and it is just going towards the receiver end. So, when we are talking about the vibrating mass and we need to just isolate the vibrating mass, that means you see here we need to design the connection of the mass or you see the entire structure or the part of the structure to the ground in such a way that there is you see whatever the untoward effects are coming out due to this vibrating masses, we need to reduce or we need to disturb the entire transmission path, so that through that we can we can say we can absorb the energy or the amplitude in that transmission feature of the excitation. So, vibration absorption on other hand refers to some additional degrees of freedom to be added, like you see in the mass or in the spring, to the structure to absorb these all unwanted disturbance. So, we can say that you see when we are using this vibration isolation feature or the design part, we need to go with the say that if we have a simple single degree of freedom system, we need to go with like a different kind of features which is to be which is supposed to be added at the point of contact or at the transmission path. So, we can see in this diagram it is pretty clear that you see we have a situation where the vibration is just generating from the machine and we need to reduce the same time. You see here we need to design such a system that the transmission should be proper, and also see here the absorption feature should be there, so that at the receiver end the things are not so dominating. So, we can see that these power which is being transmitted, first of all we need to provide the isolation exactly from the source to the ground in between. So, you see here through this isolator feature some part is being absorbed and just repulsive way towards the source, some part of the energy is transmitted through the ground, and even by putting you see some kind of obstruction in the path, even it can also provide some kind of media, through that you see the vibration transmission can be featured out. So, ultimately when it is reaching to the receiver, the path of this vibration transmission is so deviated that whatever the vibration frequency and the amplitude and the sound level, the sound power level or the energy is almost reduced by various ways. So, you see here when we are trying to keep this single degree of freedom system, we know that we have a simple spring mass like system in which you see all the forces are being balanced out by the inertia, whatever the inertia vibrating mass and the restoring forces due to this one. Or else even you see here when we are providing the damping, the forces which are being balanced out of the inertia forces are through that you see like the damping or the restoring forces. So, the meaning is very simple, that we need to provide not only the frictional feature, as you can see on the surface, the frictional feature like the Coulomb damping, the dry damping, the viscous damping is there, the material damping is there, and with the same time you see here we need to provide the spring to just control the oscillatory feature of that with the energy absorption. So, the idea here is of twofold. First, if the harmonic force is applied towards the mass, through that the movement of the ground, or you see like the vibrating masses are being there, as a result that the nearby you see the things are being disturbed, the value of the damping and the stiffness should be chosen in such a way that it can effectively minimize the resulting response of the vibrating mass. And the design which is being provided through the design of isolator which is being provided through the external system on the vibrating mass is such a way that you see here it can straightway absorb or disturb the transmission path to the ground motion. So, rather we are saying that it is a spring on an automobile or even the elastomers on the any of these exciting surfaces are just serving the same purpose. And the same time you see when we are saying that isolation needs to be there, we need to see that how the mass is being there, whether the entire system is exciting or the part of the system is exciting, whether the gear is creating the noise or the vibration, or the bearing is creating the this noise and vibration, or the entire arrangement of rotor, bearing and the gear which are under the rotating feature are creating this thing. So, we need to check it out that you see these unwanted harmonic disturbances are being created at what point, and then what exactly the transmission features are there through these robust connection of the entire mechanism. So, then accordingly we can choose this one. So, if we are talking in this case, we can straightway put the value of mass, damper and stiffness in such a way that whatever the disturbing forces which are being coming out from any source, we can choose the damper, we can choose the mass and we can choose the stiffness just to diminishes this entire vibration generation at that point. Because ultimately our main feature is not only to control the excitation vibration, but also you see here we need to isolate this propagation path also, so that the vibration or the sound level should not reach to the ground or the surrounding for the kind of disturbance. So, the motor which is mounted on say in automobile, just requiring such kind of like the spring and the damper to isolate the things. And there are various other we can say options are there which can be like adopted, not only with the this just putting the mass and the damper and can be controlled out. The options are when the path just like when it is just transmitting through that, what are the equipments which are coming in between that, means what exactly the actual path of that. And secondary, how we can just isolate the entire source in such a way that it is not even transmitting the other machinery part through their excitations. So, that is why it is very important to locate and design the isolation in the best possible way for regarding the optimum location of the isolator, because through that we can put in such a way that you see here it is not transmitting through this solid media and disturb the other equipment as well. So, there are two extreme cases which we can take here. First, the placement near the source and the placement near the receiver. So, in first case, when we are keeping the absorber or the isolator just near the source, we need to check it out that what exactly the isolation features are to be requiring, because ultimately the huge amount of excitation force or excitation energies are being there near the source. So, source isolation is somewhat more specific, and you see here it needs a typical kind of the properties at that point, while when we are designing the second case in which the receiver is being isolated, one need to go towards the shielding isolation. And the shielding isolation is straightway absorbing whatever the transmission or the the acoustic radiations are coming in terms of energy in such a way that like there is a abrupt absorptions are there at the before it is reaching to the receiver end. So, you see here either we are going in either way, they are very demanding, especially when we are just going for higher or the lower exciting features in that. So, as you can see on the screen, there are two main examples are there. First, when we are just going with the source isolation. So, you can see that in the first floor when the machines are being operating the rotating machine, they are inducing the vibration, and we need to strike on the root cause of that means the source. So, when we are striking on the source, there are clear you see the elastomers which are being provided just below the machine, and can you see here we can straightway isolate or we can deviate the path of this excitation. And the second is you see here when we are just looking that no, it is not feasible sometimes, but even after that you see the things are being transmitting in such a faster way at the low frequency excitation, then we need to just put some kind of isolators at the receiver end. You can see that the springs are being provided, so that whatever through the structural transmission, whatever the vibration level is coming, it can be even rather absorbed at this point through the shielding of the entire equipment, the shielding isolation. So, either case you see here when we are just talking about the harmonic excitations, we know that the kind of disturbance which are being coming in the forces, that is f0 sin omega t, and then you see here we can indicate that you see whatever the kind of excitation features are coming, and when we are keeping the spring or the damping, how we can design this, because we know that when we are choosing the damping, we need to check it out that what is the damping ratio, which simply gives the relation between the applied damping and the critical damping, and critical damping is the inherent feature of the system is. And then second thing is coming whether we are trying to isolate the low frequency vibration or high frequency vibrations, or even you see, because you see we just want to avoid the resonant condition in these cases. So, when we are just looking towards that, we can see that this is what you see, the forcing frequency f of t, f0 sin omega t. So, this is my forcing frequency which just gives, which just supplies, rather we can say, the force or the energy at certain frequency part. And when the entire system with the mass, stiffness and the damping, when these are being excited, then you see here what exactly the exciting features are there from this machine. So, we have the system's inherent frequency, the exciting frequency and the forcing frequencies are there. So, when we are just trying to find out the relation between whatever the transmission features, means you see x by f0, the transmission ratio, and you see here with the excitation frequency ratio, the natural frequency and the forcing frequencies, we can simply find that when we have the less damping coefficient, that means the damping which we are providing is quite less as compared to the critical damping feature of the system, then we know that the kind of excitation, the kind of transmission is such a high. You see that at zeta equals to 0.1, it is almost the maximum. But as we increase the damping properties, there itself you see the excitation source, then we know that it clearly suppresses the vibration amplitude by absorbing the energy or by dissipation of the energy itself. So, you see here the zeta 0.2, zeta 0.3, or even when we are trying to reach at zeta equals to 1, this is a critical damped feature through which we can effectively suppress the vibration at the minimum time. But again you see here we cannot go for the higher damping value just like blindly, because we need to see that whether we want an effective solution at the minimum time or just we want to just delay those things. So, you see here when the zeta is 1.5, you can see that the responses are just going, and you see the steady state response is just diminishing or just going to the end in a very long time. So, you see here with these concepts we need to check it out that what exactly the ratio of the amplitude and the force transmission, that in terms of the transmission ratio should be there, and what exactly the exciting frequency levels are there, so that we can make a proper balance and we can get. And how we can make the proper balance? By choosing an appropriate value of the damping and the stiffness, so that whatever the vibrating masses are there can be effectively controlled. So, now we can even talk in terms of the force balance equations, that you see whatever the forces which are being there at the spring level, these are the restoring forces, and the restoring forces are nothing but k into xxs, or we can say that whatever the variations are there, these are all the harmonic variations, and it is just varying with the stiffness feature of the entire system. So, k x sin omega t minus phi, and whatever the damping features are being there, that can also be evaluated based on the velocity and the available damping in the sinusoidal feature. So, we have c into omega x dot cos omega t minus phi. So, this is what you see the difference is. When we are talking about the restoring force, they are just showing the independent feature of the frequency, while you see when we are talking about the restoring force, these damping forces, there is a clear dependence on not only on the amplitude, whatever you see c or x dot is there, but also you see here it is depending on the omega, the frequency dependency part. So, we need to check it out, you see here that how means what level of you see the frequencies are there, whether we are just going for the low frequency or the high frequency excitations. So, these two forces which are being coming out from the spring and the damper can be straightway create an steady state feature of the solution, and the magnitude which we can say that you see in terms of the transmitted force is always being there from the outside displacement with the inside force excitation. So, when we are talking about this magnitude of the transmission force, then we can straightway go for the summation, the algebraic summation of these two forces, and it is simply the kx which is being there you see through the restoring, and cx which is there for this damping forces. So, when we are talking about this, the magnitude of the transmitted force through these two equipments are nothing but equals to kx 1 plus c omega by k square. and since you see we are just going with the resultant one, so it is the square root of that. So you see, like we can straightway get the transmission, that you see what exactly the transmissions are there through the entire system in terms of the transmissibility ratio, and this transmissibility ratio is always being depending upon the two main key features, what the damping ratios are, because accordingly you see here the entire system is working for the absorption of the energy or just to reduction of the vibration amplitude, and second is what is the ratio in between the exciting frequency and means like the natural frequency and the external force excitation frequencies, that is the frequency ratio. So you can see that it is absolutely varying within the transmission 1 plus 2 zeta omega by omega n square divided by you see here 1 minus omega by omega square omega n whole square plus 2 zeta omega by omega n square. So this is what you see the dependency feature of the transmissibility ratio on the two main ratios, the damping ratio and the frequency ratios. So we can say that you see like the transmissibility curve can be straightway drawn based on the characteristic feature of these two ratios. So we can say that when omega by omega and the frequency ratio is greater than 0.2, the square root of 2, or we can say 0.776. So when we are talking about you see like the one feature of that like we have the excitation feature in between the forcing and the natural frequency is greater than some value, that means the vibration isolation is an effective way, because you see ultimately we are trying to reduce and it is being effectively done. Whereas when we are saying that no, omega by omega n is less than that, where you see the transmissibility is just increased in that, means it is immediately transmitted that, where you see the amplification has been done by these vibrations, that means you see the effectiveness of the isolator based on you see here like the mobility is not an effective part. So we need to re-choose that, we need to re-choose the physical parameter of the system so that the isolation should be an effective part, or the absorber should be there in such a way that it can at least like minimize the transmission. So you can see in this diagram it is clearly showing that the vibration excitation in this part is just you see like the vibration just varying in this way, in such a way that at some point where the resonance occurs you have a maximum energy part. So there you see here we need to absorb the amount of excitation energy or the amplitude in such a way that it should come to the like the to the harmonic feature and it is being ending in an effective way. So if we are talking about say two systems, say mass m1 and m2, and the force is being excited at m2 part, and also these like the entire system is featured with the damper and the spring part, then we can say that how we can choose these things. So in this, the basic method for designing the vibration absorber in such a way that we need to first go with the 2 degree of freedom system, we need to like put the equations of motion for that what exactly the force balance conditions are there in that, and say if we are saying that the damping, whatever the damping which is being there on that particular part and the mass absorber they are just putting like the vibrating features in the entire system. In their designing you see here when we are just choosing those values, we need to see that what kind of the displacement parts are being coming out when even we are not disturbing the mass m1, on only mass m2 is being disturbed, or when we are just putting the force on the premier mass m1 and not on the secondary mass, then how the displacement are being there, and accordingly we can choose the absorber at mass m1, m2, or the source from where these displacements are being created. So with this you see here we can straightway go to the equation of motion, because we know that it is a 2 degrees of freedom system. So the matrix part is being featured out. So m1, m2, this is mass matrix with the inertia part, inertia forces with the acceleration, the restoring forces with the symmetric feature of the we can say our spring part, and whatever the force which is being excited at one mass, say if at m1 or m2. So right now we are saying that say at m1 we have the sinusoidal harmonic excitation f0 sin omega t, and when we are putting these things, we know that the entire steady state solution can be assumed along with the particular integral solution of the ordinary differential equations. So, we can say we have x and x of a with this x omega t and x0 omega t, and when we are substituting these harmonic solution, in which we can say sometimes the homogeneous solution of the steady state feature, when we are keeping that, we know that this minus m omega square plus k into x is giving us f sin omega t. So, this is what our solution we can get, you see, even the eigenvalues or the eigenvectors for such systems. So, when we are like dealing these things, we know that we have a clear amplification ratio in terms of, rather we can say, the mode shape. So, this is nothing but equals to absolutely dependence on the stiffness k plus k minus m omega square. And the same time, you see here whatever you see the featured are coming in the denominator side, like k minus m omega square and minus k s square. So, this is, you see, like the integration between the stiffness and the mass matrices in such a way that we can get how much, you see, like the amplifications are there, or how much, you see, like we can say the displacements are there right from x to x a. So, when we are talking about the final displacement x, it is nothing but equals to the k a minus m omega square, which is being adopted there, into whatever the force excitation which is being input, divided by k plus k a minus m omega square, the inertia feature, and into k a minus m omega square. So, this k plus k a and, you see, like the minus m omega square are being featured out in such a way that we can simply control the displacement of the entire excitations. So, we can see that even the k a or k r is just to be chosen in such a way that the k a minus m omega square should be 0, or else we can say that the k a by m a should be equals to omega square. In other way, we can say that if we want to get the steady state response for the primary mass m, it can be 0 only when x equals to 0, or else, you see here, when it is being excited at the square root of k by m. So, if any added mass which is being m a was there, you see here, is absolutely tuned to the driving frequency omega, obviously, you see, the amplitude of the steady state response of the primary mass is supposed to be 0, because the entire energy is being absorbed by this added mass at the tuned frequency, and the absorber mass is effectively applied to the entire, you see, like the source where it is being required. So, that is what, you see, one of the system is, when we know that the system is exciting at the higher harmonics mode, the added mass in terms of the absorber feature is an effective part, because, you see, we know that the flywheel feature which we are just applying there is one of the effective way in absorbing the entire shaft vibrations. So, we can say that, you see, like in general, when we are talking about the vibration isolation, we need to see that what exactly the source, what is the transmission path through which the vibration transmission is there, and what is the receiver at which, you see, the noise level and the vibration excitations is coming. So, the objective of the vibration isolation is just to reduce in a very, like a specific part or the entire structure by adopting the mass, the spring, and the damping appropriately. So, you see here, like the entire magnitude of these vibration is being like reflected by the excitation frequency and the amplitude in such a way that we need to design our isolator in this way. So, the most common way to accomplish these things by like providing the discontinuity or by providing the reduction at the source by like appropriately choosing these vibration isolators. So, we can say rather the steel coil spring and the rubber isolators both are being effective, we can say, like the media through which we can achieve this much accuracy of the vibration control. So, in this lecture we discussed about the basic frame work of the vibration isolator and the absorber, set in which conditions we need to choose the mass as a vibration absorber, the isolator or the damper, even the elastomeric dampers through which, you see, we can provide the integrated part of the like we can say the spring and the damper as well. So, in the next lecture we are going to discuss about the real application that, you see, like in all these, whether we are talking about the vehicle or we are talking about the industrial machinery, that what are the real feature of the isolators and where we need to apply, what is the optimum location where we can straightaway strike out the vibration isolation feature. Thank you.